Hi, everyone. My name is Raresh. I work as a tech lead for N26. In case you don't know us, we're a digital bank. We have offices across all of Europe, so in Berlin, Barcelona, Vienna, small office in New York. Obviously, we're hiring, so if you're looking for a job, let us know. Okay, today we're going to talk about resilience service-to-service calls. More specifically, we're going to talk about it in the frame of Hystrix being deprecated. So if you come from a JVM world, you probably know Hystrix. It's a very common circuit breaker library from Netflix. And sometime in October last year, Hystrix was actually deprecated. So this pushed us to actually reevaluate why we were using Hystrix in the first place, whether or not we still need to find some alternative for it, and what are these alternatives. And this is what we came up with. So the first question we asked ourselves is, come on, this is 2019. Who still does synchronous service-to-service calls? Like, everything is event sourcing, CQRS, Kafka, whatever. So the first question we asked ourselves is this some direction in which you want to go? So I'm going to ask you as well, like, how many of you have a primarily synchronous service-to-service call, microservice, infra? Okay. How many of you have a mix of both, so both synchronous and like some sort of, okay? And how many of you have drunk the event sourcing Kool-Aid, Kafka everywhere? Okay, cool. Okay, so looking at the hands being raised in the air, I think that it's pragmatic to say that a combination of both solutions is actually what you should go for, because like going fully asynchronous also has a lot of potential side effects, a lot of extra complications, and it's not for everyone, especially for like younger startups and companies that are not really, really mature. Okay, so then we asked ourselves, okay, what is a cascading failure? What is it we were trying to actually prevent with Hystrix? This is a very vague question. What happened here? I think it's not very easy to see this pink line, but what do you think happened here? And I'm keeping this intentionally vague because the question has a very simple answer, but... Sorry? Oh? I'm sorry, okay. Queries? Sort of. New deployment? Yes. So the first and probably the biggest condition for all problems is change. We all know that change is inevitable in our industry, so we couldn't really say, okay, we're going to close up shop, everything is going to run as it is, and we're not going to change anything. That's absolutely not an option. So what happened is that someone deployed this change. The story behind it is we had a cache, and our product said, okay, like this cache is usually serving stale data, or is serving stale data quite often, so let's try to go to the source service, fetch the data, and fallback, use the cache as a fallback. But the person who implemented this actually reused the update method that would go to the service and store stuff in the cache. So this resulted in a lot of write operations to the database, which resulted in this spike that you saw earlier. Obviously, sources of change can vary. You can have new rollouts. You can have intentional traffic that drains from one DC to the other, many, many situations. This is actually a zoomed-out version of the same incident. So as you see, the initial thing happened when we released the new change. After that, we ran with a lot of write IOPS, and then suddenly something crashed. What happened here? Sorry? No. Rollouts are marked with this pinkish line, so it's not another rollout. Sorry? Warm-up? No. No. This is credit balance from AWS, or more specifically, burst balance. So AWS gives you a specific number of write operations that you can have that surpass your regular operations. And if you go past that for a very long time, they just like throttle everything. So basically, we were being a really bad citizen in the RDS world, so they just decided to throttle us. So, sorry. So yeah, throttling from your cloud provider, service providers is one of the conditions that can actually trigger such a failure. Okay, the traffic for the request per seconds for this graph is usually directly proportional with the number of logins we have in our system. But in this case, you have all these spikes happening everywhere. What do you think is the root cause for this? Pardon? Maybe as a hint, look at the time when these are happening. No? Yeah. So it's cron jobs with an emphasis on this puppy here, which is a bit different than the rest. So yeah, it is cron jobs. It's basically just a job that takes some files from some partner, processes them, and moves on. There are so basically what I'm trying to show you here is that bursty behavior, burstiness in general in traffic is also one of these conditions. With this particular spike as a special case of this, because we actually received a way larger file than we anticipated in that situation, and it caused a lot of trouble in our microservices. So I named this in general entropy, so it's all the random stuff that happens to your microservice architecture. So it can be like burstiness, it can be DDoSes, it can be, I don't know, spot-ins taking down some instance from you. There's a lot of randomness everywhere. Again, this is something that we have to work with, and we have to work with the assumption that anything can fail at any time. Okay, so the common denominator for all of these is the fact that they all refer to a finite set of resources, right? Like we always work with resources. Resources are limited. Some stuff that can happen if you run out of these resources, and won't go into too many details about why and how. But just so you know, this is something that happens. Okay, so resource starvation. Let's discuss how these resources are actually interconnected. So let's assume that you just finished DevOps Barcelona, and you go back, it's Friday, it's a really sunny day, and you decide to tune your garbage collector at Friday, I don't know, at 4, when everybody's away from the office, but you decide it's a really good idea to do this. So you decide to tune it, because you saw some really nice presentation here at DevOps. You do a poor job of it, because you just base it on what you saw at DevOps and not on your research. So this causes increased CPU, because you have increased garbage collection. This will result in slow requests. This will result in you having to process more requests, which in turn will grow your queue, which will have you use more RAM, which means that you will have less RAM for stuff like caching. Also, more RAM will probably result in more garbage collection, which will kind of start this cycle and amplify this cycle over and over again. You will have a lower cache hit rate if you have less RAM for caching. You will have more requests going to like the backend that was actually the source of data for this cache. And then all hell breaks loose, fires everywhere on a Friday afternoon. Lovely. So this is something that results. I really hope that this thing renders colors correctly, because I really tried hard to reproduce the blue screen of death. This is the 2010 edition. So you all know what happens when we have one of these situations. Instances get taken out of rotation. You have 500s everywhere. Health checks failing. CPU is maxed out. Everything like goes to hell. Okay. So when this thing starts happening, imagine you have this setup where you have a more or less even distribution of load to your two instances, but one of the instances suffers one of these complete meltdowns. So it's going to be taken out of rotation, and all traffic will actually go to the other instance, which, again, makes it more likely for this instance to fail. So it's one of the situations in which you actually get a cascading failure. You just like have load redistribution across all healthy instances after one instance died. If this healthy instance is unable to handle the load, you'll just get this problem propagating everywhere. Okay, another such situation. You have these 500s here, and these 500s actually did not, did not come as a result of increased traffic, but they caused increased traffic. And this is actually because we started retrying again, and we started retrying in an uncontrolled way. So basically, what you see here is usually referred to as a retry storm. You have some service that's being unhealthy, and it's actually triggering a lot of retries, which actually makes it more likely for the service to continue being unhealthy and to be buried deeper and deeper into this mess, and it will result in a lot of mess. Okay, this is also interesting. So what is happening here is that you see latency slowly growing. What's happening in the example above, it's a service that's calling the service below. And as you see, there's like a more or less even number of TCP connections because we're using connection pooling. So like we're just reusing connections over and over and over again. But when latency starts building in, these connections will be occupied because of the latency. They're like just going to wait on I/O over and over and over again. And what happens is the connection pool actually creates new connections, and you see this like huge surge in new connections being created, which, besides the fact that it actually causes some overhead because connection, like the TCP handshake actually has a pretty big CPU hit if you do it at scale. It's also something that's a symptom for cascading failure in the making. Okay, this is also, I like to call this take your lambs to the slaughter, because it's a situation in which you have a lot of traffic, a lot of instances with resources maxed out, so CPU is maxed out, memory is maxed out. So what you do is your auto-scaling kicks in, and you just slowly add new instances. But the problem is that you're slowly adding new instances. You're not doing it fast enough to actually take care of all this increased traffic. So what happens is that you have this nice instance, it's booting up, maxes out immediately, crashes, gets taken out of rotation. So basically, you don't really fix anything. The thing to remember here is that you actually either need to remove the traffic, block it somehow really quickly, or actually scale up really, really quickly, because otherwise you won't help and you're just going to send more instances to the slaughter. Okay, so now that we've seen a lot of problems that can occur, let's look at what we can do to fix it. Okay, so I'm coming back to my initial question, which was related to synchronous calls versus asynchronous eventual consistency calls. Basically, this is colloquially known as orchestration versus choreography. Orchestration is when you actually use synchronous service-to-service call to propagate information across your infrastructure. Choreography is something like, okay, you publish an event to your Kinesis, Kafka, whatever, and after that, you have subscribers that subscribe to these topics and take actions based on these. If you can move more flows towards choreography, it's better. It will help you deal with a lot of these problems that stem from cascading failures. So it's easier to apply back pressure in this situation. It's easier to make sure that you don't lose events. Obviously, if you're managing your infrastructure properly, it's just like way easier to handle. At the same time, all this setup involved in a choreography kind of architecture is expensive from other points of view. I think there were some really good talks that discussed the pains of, I don't know, managing Kafka, all the overhead of having to deal with all these clients for subscribing to the topics and so on. Like, I'm not going to go into too many details, but sometimes it can also be impractical. That's why we also have valid use cases for orchestration. Okay. Another thing we have to take into account is capacity planning. Like, okay, we need to make sure that we have enough capacity, enough resources that we were mentioning before to deal with all the traffic. But do we still need it in the age of the cloud? Who here does like really intricate capacity planning on a regular basis? Okay, cool. So there are completely valid use cases to do it, but at the same time, in many cases, it can be impractical or just overly expensive to do it. First of all, it's not sufficient. It's not the only thing that saves us from cascading failure. Obviously, it's something that's needed, but not enough. Also, being accurate, especially for new services, is super hard. Like, I have yet to see someone who managed to actually get their capacity planning right from the get-go, because you have fluctuating traffic patterns. You don't know exactly what the traffic patterns will be. You don't know exactly how much memory or RAM a specific request takes. So it's very, very hard to predict. So my advice would be that if you're at the scale where you can afford it, just over-provision the hell out of it. Watch the traffic patterns for a couple of days, and after that, scale down to limit costs. But otherwise, try not to invest too much time in upfront capacity planning. What you should invest a lot of time in is automated provisioning and deployment. So cattle, not pets. I think you've heard it a lot during this conference. I'm going to repeat it because it's really important. Try to make it super, super easy and super, super cheap for you to take instances in and out of rotation, scale them up, scale them down. Don't create all sorts of weird dependencies between instances of the same microservice, because it's just going to put you in a whole lot of pain. Also, auto-scaling and auto-healing, another thing that's kind of related to this. If you this will also help you reduce cost, because you can scale down automatically when your traffic is low, scale up automatically when you have high traffic. So it basically just like does automated capacity planning that responds to your traffic patterns. I'm going to go back to publisher subscriber and say that even here, even with capacity planning, implementing more stuff in the publisher subscriber pattern helps, because you can apply back pressure. So if you have growing traffic, you can just process a specific amount of it, and you won't lose events. Yeah, sure, like there might be some lag in your infrastructure, but you might be able to handle it in a better way. Also, super important, SLIs and SLOs. Basically, discuss with your business what are the things that you want to optimize for, and actually make sure that those things are fast, make sure that those things have enough capacity allocated to it. And if you don't know what your SLIs and SLOs are, and if you don't know what's important for your business, then you're in trouble, because you're going to try to actually optimize for everything. And this is the biggest point for the case when you do need capacity planning. So I know there are many of you who maybe work in like companies which have huge amounts of traffic. There you might actually want to give some thought to capacity planning whenever you're introducing a new service. So in that case, the first requirement is to actually base it on business requirements. Another important thing is to focus on critical services. So if you draw a map of dependencies between all your services, you will see that like some of your services are highlighted as something that a lot of the other services depend on. So focus on capacity planning for that. Don't overdo it, but try to come up with some nice handwritten calculations for how much capacity you need. Handwave the rest. Over-provision, do whatever you want, but like focus on the critical services. Also watch out for seasonality. So all the Black Fridays and the Christmases and everything. Even if you're not a retailer, because we've actually had some situations where there were so many retailers in our co-location in Amazon that we actually couldn't scale up. They actually pre-reserved so many resources for Black Friday that we're in a situation where we were just left out with the number of instances that we had at that point in time. So watch out for that, even if you're not a retailer. Okay, and another thing is, when you calculate this capacity, the needed capacity, don't focus only on requests per second, because requests per second is a bit of a red herring. Because requests are not all created equal. They're not all like, they don't put the same amount of strain on your infrastructure. For example, if you have a health check compared to something that does a lot of CPU-intensive operations, it's not exactly the same request. So try to always translate it into some common metric, like CPU is a good one, because usually CPU is also related to memory, because on garbage-collected platforms you have higher memory that usually determines higher CPU. So try to use that to translate your request per second in. Okay, this is something that I don't have too much experience with, but I'm sure that it's something we have to explore, and I think so should you. Like, chaos testing is something that was championed by Netflix. It's basically the practice of intentionally introducing problems in your production code in your production environment, like, I don't know, intentionally removing some instances, introducing network latency in your live environment, mind you. And I think it goes together with what Google were doing. It was mentioned in the previous talk. Google were actually doing something similar when it comes to some particular service that was so stable that everybody thought it couldn't fail. So they actually started to intentionally create this expectation in people's mind that this service can actually fail and they should protect against it. So check it out. There's a lot of information on the internet. This is not to talk about chaos testing. Retrying. So retrying is a really, really thorny topic. First of all, what makes a request retryable? What can we even retry? And I would argue that idempotency is key in this particular thing. Like, if you don't have idempotency, please add it to your endpoints, especially if you're some sort of public API provider that other people integrate with. Idempotency is super important because if you don't know whether or not you can safely retry something, then you might end up with a situation where a request timed out. Then what? You have Schrodinger's request. It might have gone through, it might have not gone through, you don't know. Please, 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 I beg of you, don't do gets with side effects. Don't do funky stuff. Don't introduce this weird hack because it's convenient, but it's semantically wrong and it goes against like all REST and sanity principles. It will just create false expectations. People will misuse your API and stuff will go bad. Also, please try to keep your stuff stateless. I know that maybe 5% use cases where there are some use cases where you actually need to have some sort of sticky sessions or some sort of stateful APIs, but if you can prevent it, please do it, because otherwise you cannot really properly do retries. And timeout retrying, that's another thorny topic that we're going to discuss later. Another really important thing to do when you're actually retrying is to make sure you introduce jitter in your retries. So these are two graphs of someone retrying with exponential backoff. So if you're thinking that exponential backoff is enough, think about this graph. What you're seeing here is that it's taken from an Amazon article. It's just a synthetic experiment where someone decided to, at some point, let some requests go through, but in the end, all the other requests are going to fail. So what you see here is that the services are exponentially retrying, but they're retrying and they're forming these clusters, this burst traffic of retries because they're more or less aligned on the time when they're doing these retries, which means that during all these bursts of traffic, you're overloading your service again, making it highly unlikely for it to become healthy. Whereas if you introduce jitter, which is basically just randomness in the amount of time you wait between your retries, you get this nice even distribution of distribution of requests, which is a more manageable load for your server, for your unhealthy server, which means makes it more likely for it to recover. Okay, what else can you do? You can assign retry budgets. So everybody has this thing where they retry at most 3 times. Yeah, it's a really good practice, use it. But I urge you to also consider doing per client retry budgets. So let's say that you can retry, or at most 10% of your requests can be retries. Because if more than 10% of your requests are retries, then it means that you're retrying quite often, which means that most likely your upstream service is not healthy, which means that retrying won't make it healthy necessarily. So try to limit this and try to do throttling of retries on the client side. And this brings us to timeouts, which are my favorite topic that's often overlooked. So take some time to let this diagram on the right sink in. Basically, you have service A calling service B with a 3-second timeout, service B calling service C with a 2-second timeout, and then service C calling service D with a 5-second timeout, and this thing actually times out. So what will happen here is that Service C maybe will retry, but service B will have timed out a long time ago and is no longer interested in the result that is produced by service C, even if the retry succeeds. So basically, what you end up doing is doing a lot of unnecessary work, and this in a situation where you have a lot of problems happening across your infrastructure, and a lot of these retries happening, even though the result is not really necessary for the downstream services, then you end up in a world of hurt and a lot of unnecessary load on your services. So this is massively amplified by nesting. What's the solution for removing nesting? Publisher subscriber again. So this is one situation where it's again helpful to just like rely on some message bus and not have like service A calling service B, calling service C, calling service D in an endless nest. Also, there's this thing where I put this a bit reluctantly, maintain discipline when setting timeouts, because it's very, very hard to actually maintain discipline when setting timeouts. Let's say we have another service coming from another flow that can afford to actually call service D with a 10-second timeout or whatever. As you have more and more nesting, it becomes harder and harder to set meaningful timeouts for these calls. So yeah, you can try to set like progressively smaller timeouts as you go deeper into this nesting graph, but I don't think you can do it in a meaningful way if you have too much nesting. There are some frameworks. I think gRPC does propagation of timeouts, which is a better idea. But this means that you have to like kind of do this consistently across all of your backend infrastructure. So if you can do it, do it. It's just hard. And for the love of God, avoid circular dependencies. This makes it so much harder to argue about any of this. Like imagine that service D actually also calls service A to get some other user data, and then what? It's just a mess. Okay. Another form of throttling is per client limits. So remember what I told you when we were discussing about capacity planning, which is to calculate the capacity using some sort of common metric that translates into your hardware resources. So you can actually use the same metrics to calculate specific client budgets, let's say, for each of your clients. So you can say client A can use X% of the CPU for service B for a specific time period. This sounds really nice and cool, but it's also very hard to implement in practice because you actually need some tool to aggregate how much I don't know, CPU, some particular client used across all your infrastructure, across all your services. So if this is way too complicated to implement, just go for some basic limit of like, client A can call me 500 times per second. It's still better than nothing, and I completely encourage you to do this because it's going to make everything way more robust. And it will give services a way to push back when clients are being abusive. Okay. And finally, we're reaching circuit breakers, which was kind of the thing that started everything. So if you're familiar with the concept of a circuit breaker, basically it's something that sits between service A and service B, between your synchronous calls. If everything goes fine, the circuit breaker is closed. You can imagine it like a light switch. If at some point some of the requests start timing out, they start incrementing a counter for timeouts or for failures in general. And once this counter hits a specific value, then the circuit is open, which means that requests are not let through, which means that you're either serving like, I don't know, some cached value or some fallback value or just returning an error, but the requests are not going through to service B because the assumption is that service B is unhealthy, and piling up more requests on top of service B will not help it heal. So this is actually the pattern that's implemented by Hystrix, and this is like the deprecation of Hystrix as a library for circuit breaking sparked this whole conversation. because Netflix is such a cool company, they also came up with a solution to it. They're advertising it as adaptive concurrency limits. Basically, it's an algorithm based on TCP congestion control, and I'm going to try to do a good job at explaining it. But the assumption is that, okay, you have concurrency, which is the amount of requests that you can actually serve concurrently on a specific service. Anything that goes above this concurrency limit is going to cause your request to queue, right? Queuing will usually be translated into higher latency, and this is the assumption that they're doing. So basically, this library will kind of check whether or not there's latency forming in the call, and after that, if there is, it's going to start throttling some of the requests. It's going to reduce the concurrency limit. Basically, you have this gradient, which is the ratio of what is the concurrency limit if you don't have any, what is the latency if you don't have any load in your, like, 1, 2, 3 requests, like in your regular scenario, versus what is the latency that you're currently reading. Ideally, this would be this ratio would be 1, right? You want to be as close as you can to the latency of no load. If this is changing, so if the latency RTT actual grows, it means that this ratio will become significantly smaller than 0, which will mean that multiplied by the current limit, it's going to drop the current limit and reduce the window of how many requests are let through. So basically, what you'll end up with is like this nice sinusoidal graph of like, trying to push the limits of how many requests you can go through. After that, you throttle it a bit. After that, you move it a bit more. So like, in the end, it will tend to approach the actual limit of what your service can actually handle. Okay, so what if all these things fail? What if all the resilience measures we're trying to take don't work out? Then we have fallbacks. This is actually a diagram of user solutions in reverse user crappiness order. So probably the best thing you can do is to serve a cached request. Most of the time, users won't even notice something happened. But depending on how you set up these things, caches can be difficult to maintain, so it might not be the cheapest way to deal with fallbacks. Dead letter queues are also a nice alternative, especially if you have write. So just park the request on a dead letter queue and have someone look at it when the service is healthy. A hard-coded value is also good. So for example, if you look at Netflix could have some sort of service that returns movie recommendations for you, but if the service is down, it can just return a hard-coded list of most popular movies like, I don't know, Avengers and all these things. It's not great, but at the same time, it's also not something that the users will perceive as terribly bad, depending on your movie taste, of course. And the worst thing you can do is actually to just return nothing or an error or something. Please try to avoid this, and please try to discuss with the product owners what is the cost of having, for example, a cache for this versus what's the potential user dissatisfaction. And it's basically just a ratio, and you'll find the solution somewhere in the middle. Okay, so tools for improving resilience. I promised you some alternatives. Here they are. Oh, wait, this is Hystrix. So yeah, we're going to start with Hystrix, just briefly mentioning how it works for people that might have not seen it. So Hystrix is basically just a jar package, a jar library. It will sit in your service code, and all of your third-party requests will actually have to go through this through a configured circuit breaker. You have to configure these circuit breakers independently for each request. It's a bit cumbersome, you'll see later, but it also has some nice advantages. So what it offers is it does have like some sort of timeout support. So timeout is considered an error in the Hystrix world, and it will amount to the error counter that I was mentioning earlier that will end up opening the circuit or closing it afterwards. It does have circuit breaking, obviously, and it has some really nice support for fallbacks and response caching. So it's really easy to actually have to implement some hard-coded value that you return to users as fallback. This is what it looks like. It's not great. It's a bit like complicated, especially given the fact that you have to set up one of these commands for every one of your calls. But it does have great observability. So there's this thing called, I forgot what it's called. It's Turbine, yeah. So there's this thing that you can have that aggregates all the metrics from all of your Hystrix circuit breakers, and it produces these cool graphs, but yeah. You might not need those. It's relatively easy to test. I added some caveats there, but like I'm not going to spend too much time on it. And yeah, this is why you should or you shouldn't adopt it. Obviously, the main reason why you shouldn't adopt it is the fact that it's no longer supported. It's pretty stable. It hasn't had a lot of work done in recent years, but at the same time, if there is any security vulnerability, it's not going to be patched. So be aware of that. Not language agnostic as well, so depending on how heterogeneous your backend microservices are, this might prove to be a problem. At the same time, on the flip side, it has really good observability, and it's also quite easy to test. But another problem that we're facing, and this is something that pushed us to look for other solutions, is the fact that it's super hard to enforce it on the calling services. Basically, it's very hard to make sure that all the service authors that are calling your service will actually have this built into their calls to your service. And we tried to create some libraries for that. We tried to actually have like some fat clients, APIs for our services. This comes with a huge number of problems. More specifically, Hystrix has a lot of transitive dependencies. So whenever you would use one of these fat clients, you would drag along a lot of transitive dependencies that will end up conflicting, having version conflicts with your direct dependency, your service's direct dependencies, and it's a huge mess. So people really hated me for this in my company because I was one of the ones that created this SDK client, whatever. So I was compelled to fix it. So let's look at the first alternative, which is Resilience for J. Resilience for J is actually super similar to Hystrix. It's an open source alternative that Hystrix gives you as an alternative to, actually it's not Netflix who authored Resilience for J, but Netflix is promoting it as an alternative to Hystrix. It's, again, like also a Java library, super similar to Hystrix in terms of setup. It has a lot of features. Like it's super feature-rich, and they're also working on adaptive concurrency limits. But they literally have modules for everything. And this is what setting up such a Resilience for J circuit breaker looks like. So it's basically just an implementation of some decorator pattern, and you just wrap as many decorators, like a Retryer decorator, a circuit breaker decorator, on top of one another. It's very nice, very modular, really easy to use, although the code might not show it, but it's quite nice. It has great monitoring support. You have all these events that you can hook up to and like send whatever metrics you want. It also has some built-in support for Drop Wizard, Prometheus, Micrometer, everything under the sun, basically. So you won't have a problem there. Also, testing is pretty much the same story as Hystrix. It's a library. You can unit test it. You can do integration tests. If you have this request level caching enabled, it calls for a bit of special attention, but otherwise, more or less, it's more or less testable and easy to use. So, what does it have going for it? Observability, a gazillion of modules, and the fact that it's quite popular means that it's also getting a lot of new modules every day, so you're going to have like a ton of features. It's easier to configure than Hystrix. And it also has, really importantly, it has way less transitive dependencies than Hystrix. So if you end up building clients for your libraries, you'll end up with less fat clients and less dependency version problems. It's also not language agnostic, and it's also forcing you to build those clients that I also mentioned. Envoy. So Envoy is a very popular sidecar, basically. It's a proxy that you install next to your services, and that can route requests going in and out of your services through it. And it also has pretty excellent support for all sorts of service resilience features. Basically, it has support for retrying timeouts, rate limiting, and they're actually working together. Lyft, who is the main maintainer of Envoy, is working together with Netflix to bring adaptive concurrency limits into Envoy as a first-class citizen, which is great. What is a bit tricky is this. It's like configuration is super verbose, as you can see, and if you want to apply the same circuit breaker configuration to all of your routes, that's fine, but if you want to go more and more granular, then you're going to end up in having some problems. So then you will have to deal with some sort of automation. You can either go for, if you decide to use static configurations, which is possible, then you'll probably need some tool to auto-generate this, to test it, and it's not the easiest thing to do. So what everybody does, especially if they're building, if they're using Envoy at scale, is actually going for calling the APIs for dynamic configuration. They have this really cool, rich set of APIs that you can use to dynamically configure Envoy. Unfortunately, yeah, you also need some sort of oversight of all of these things. What is the current state of my circuit breaker on Envoy? What is the current state of my configuration on Envoy? So this is where having a more mature control plane like Istio will really help you manage all of this complexity. On the flip side, observability is great. Like this is one of the things that's very, very heavily emphasized in the Envoy design principles, and as a result, they have a ton of metrics. You can get anything you want. You can send it to any tool you want. It's great. And it's relatively easy to also detect events like circuit being opened, requests being throttled, la-di-da. Testing is a bit weird. You basically have to boot a Docker container that has Envoy, and after that you have another container that has your machine and try to do some sort of end-to-end-ish integration tests. But it's not impossible, and it's totally doable. So what it's got going for it, and it's super important, is the fact that it's easy to enforce across all clients. So remember the thing that I was telling you, that it was very hard for us to tell every service consumer, hey, please make sure to configure Hystrix. Hey, please make sure to call us with some resiliency features built in. Envoy makes it easier because you just configure it on the sidecar level, and after that, that's it. Operational complexity is definitely something that's to be considered, and if you don't have a mature infrastructure, a mature SRE team, that's something that might bite you. Also, depending on how your company is organized, it might fall somewhere in the middle of the SRE team and the backend team, so you might not know who exactly owns this configuration. It's also the fact that, you know, like some of the circuit breaker configurations are more business logic, whereas some others are more SRE, so it can prove to be a bit of a communication hassle. Okay, concurrency limits. Last thing, and this is the official solution from Netflix. Basically, you can use this to ensure both clients and servers are protected. And this is really nice because you can also say, I can, as a service provider, can say, hey, I'm going to protect myself against abuse. I don't care what the clients do or whether or not they implement and they configure some sort of circuit breaking library, so this is cool. It only does this. It's the only solution that they have. This is what it looks like for a server-side configuration. It's, as you see, it's not as verbose as the previous solutions, and it's actually pretty easy to configure. It's a bit magical, a bit too magical. Observability is also there. This code is probably a bit more complicated than it should be, but there's event hooks for everything. You can send all sorts of information anywhere. You can detect when the current rate limit or the current concurrency limit. The problem is that it's very, very, very unpredictable. So it's going to be hard to test and predict the behavior of it. So that's the main kind of thing that you can encounter when using this. So yeah, there's that. So what did we go for in the end? Any guesses? Yay! So this is a comparison of all of these things. We actually analyzed 2 more tools. You might be surprised to see gRPC there. gRPC actually has a very, very ambitious RFC out for how to build a lot of resilience features into both the client and this stub server that they generate. Unfortunately, this never made it into production, and we decided to skip it. Sentinel is kind of like a Hystrix from Alibaba. Unfortunately, all of the documentation is in Mandarin Chinese. So we decided that it's probably best to not go for it because we don't have that many Mandarin Chinese speakers in the company. So yeah, Envoy is the winner, mostly because of how easy it is to enforce it, and also because we have already adopted it in our backend. The runner-up is Resilience for J because we still need to have something for doing retries, and we didn't want to put this on the Envoy level because I'm being kicked out. Okay, we didn't want to put this on the Envoy level because it's going to be way harder to configure. Do we have time for questions? Okay. Okay. Do we have any questions? Okay. Thank you.